Hello everyone, today we'll be presenting our statistical process control study of ion milling process simulation via laser cutting of acrylic plates. Today's agenda will comprise of a quick introduction, fabrication method, data gathering method, data analysis, study inference, and the objective of the study is to simulate the ion milling process, which is often utilized to etch silicon wafers during their fabrication process. The simulation is achieved by using a laser cutter to make cuts along an acrylic plate. The chosen output variable for the study is the width of the cuts made by the laser cutter. The width are analogous to the etching width of an ion mill when etching on silicon wafers. For this study, the null hypothesis claims that adjusting the speed of the laser cutter in the horizontal direction has no effect on the average cut widths of the acrylic plates when performed under nominal parameters.
Okay, so for the fabrication method, we basically used a laser cutter, and it was a universal laser engraver with the parameters of a 2.0 lens, 75 watts, and a CO2 laser. We also used Adobe Illustrator to create the pattern that we would be using. So on Adobe Illustrator, we basically created two different patterns in which we would basically create our little samples. For the first one, we created a horizontal cutting pattern, which is 3-inch long lines in red and distributed among 0.1 inch spacing and aligned it to the left side or right side. And then from that, we created 20 vertical lines to cut each piece through, and that is 1.5 inches long with distributed space of 0.15 inches going to the top. For the horizontal depth cuts, in which we would mimic ionic milling, we basically ran 100% power at 3.1% speed with a points per inch setting of 1,000. This created our first 40 controlled set, and then when we moved forward to the modified or altered set, we created a modified parameter of the speed to increase to 10%. For the vertical line cut throughs, we basically ran it at 100% power at 2.8% speed at a 1,000 points per inch. For the process, we basically got a 1/4 inch thick piece of acrylic, placed it to the top left corner of the laser engraver, and performed the depth cuts accordingly, letting the piece cool off, then performing the through cuts, and then removing the samples. As you can see in the image, that's our gathering of the samples. So to our very, very left, you see the pattern cutouts for each sample in the cutter, and then on the very right is the UI that we used. Here are two videos of the cuts happening.
For data gathering, we took the 60 samples that Clarence made with the laser cutter. Each sample had 4 cuts etched into them by the laser. These will be our subjects for the gap width measurements. The gap width measurements were taken using a free software called Digimizer that would create a length value in pixels. We used a loaned A005 5 megapixel 500 time magnification handheld microscope loaned to us by Professor Lee. After several iterations on different samples, we found that a 200 times magnification and a 20 millimeter gap from the sample to the lens would allow us to acquire clear enough images to distinctly make out the edges created by the laser cutter that would be used as markers for distance measurements in our image software. We created an L-shaped acrylic part that would be used as a jig for alignment with the camera through all of our iterations. It was found through some analysis that with this given distance to the microscope as well as its magnification, there would be 2.58 pixels per micron. This number would allow us to calculate the gap width for all of our samples. For each of our 60 samples, 4 measurements were taken per sample. Then the next sample was rotated in with no adjustments to the microscope magnification, and the positioning was done using our L-jig. So on this slide, we can see our alignment bracket in the top left. In the center, the distance measured to the sample in order to create repeatable measurements without changing the magnification. To the right, we have an image of one of our samples that was used for measurements. We can see the gaps here with the edges we chose to use for the Digimizer software. In the bottom left, we have an overhead view of the measurement station with multiple samples on tape as well as the mount for the microscope. On this slide, getting into some data analysis, this chart shows all 60 sets of our 4 cut samples. The first 40 sets had no process change in terms of the laser cutter, as Clarence mentioned earlier. Our process change came in the last 20 sets of 4 samples, which clearly start to bring the measurements outside of the normal distribution, which our control limits will be able to catch.
The X-bar and variance control charts were generated for the mean of each subgroup of 4 samples for a total of 60 subgroups. In generating the control plots, we found that the average cut width for our process under nominal input parameter is 0.76 millimeters. The lower control limit for the X-bar chart is 0.65 millimeters, and the upper control limit is 0.87 millimeters. Similarly, the X-bar and range control charts have very similar behavior and trends with the sample mean. We can see that in the beginning, the process behaved fairly random and is within process control. However, after introducing the 20 samples where we changed the speed, the process was no longer in control. 18 out of the 20 additional samples were below the lower control limit.
ANOVA sum of the square was used to understand the variance of our data, with the hypothesis that the mean of the group are equal. And from our calculation, we found mean square of group is 0.028, and mean square of between samples is 0.012. And from the calculation, we get F to be 2.35, which is greater than the F critical, which is 1.359. Thus, the hypothesis fails.
To recall, the null hypothesis of this study states that adjusting the speed of the laser cutter in the horizontal direction has no effect on the average width of the cuts. However, from our ANOVA sum of square analysis, we see that the calculated F statistics is greater than the critical F statistics, which suggests that the width means across the groups are not the same, thereby indirectly supporting for the rejection of the null hypothesis. Additionally, in analyzing the control charts, the shift in process mean suggests that the change in the laser speed was the cause. A plot of all collected samples against a normal distribution probability plot also shows that our study follows a normal distribution, and thus our analysis methods are. In conclusion, for our simulated process of ion milling using a laser cutter, we found that with nominal input parameters, the input mean cut width is 0.76 millimeter. When adjusting the speed of the laser cutter in the horizontal direction, we can see from the control charts that there is a shift in process mean, and the process was no longer in control. We can attribute this change in the laser speed as an assignable cause to the process mean shift. The rejection of the null hypothesis is further supported by the F statistic comparison from our ANOVA sum of square analysis. This concludes our statistical process control study. Thank you for listening.